Hi everyone, my name is Andrew Rudichenko, and today I'll be presenting my work, mWhisper-Flamingo for multilingual audiovisual noise-robust speech recognition. This work was conducted in collaboration with the following authors and was accepted for publication at IEEE Signal Processing Letters 2025. Automatic speech recognition, or ASR models, are great for transcribing audio. However, they often struggle with background noise. Audiovisual speech recognition, or AVSR, is a classic method which combines audio with lip-based video and can improve the performance and noise. However, most methods are only trained and tested on English videos, and one reason is the lack of large-scale multilingual video datasets. In our previous work, Whisper-Flamingo, presented at Interspeech 2024, we proposed a method which combined strong pre-trained audio models with a lip reading model. Specifically, we used Whisper, a multilingual speech model pre-trained on 680,000 hours of audio, and AV-HuBERT, a lip reading model pre-trained on 1.7 thousand hours. We integrated the visual features into Whisper's decoder using gated cross-attention layers, and we achieved state-of-the-art performance on English AVSR. However, in that work, we only used English video inputs. We used Whisper's multilingual text decoder for English text translation, but we didn't use Whisper's multilingual audio encoder yet. Whisper was trained on audio in 100 languages, so we wondered whether we could train a multilingual version of Whisper-Flamingo on videos in different languages. In this work, we propose mWhisper-Flamingo for multilingual videos. We use the MuAViC dataset, which contains videos of TED Talks in 9 different languages. The goal was that the audiovisual model should be better in noisy conditions than the audio-only model for all languages. However, when we applied the default training setup from Whisper-Flamingo, this method worked well for English, but not the non-English languages. Specifically, the performance on those non-English languages was the same in the audio and audiovisual scenario. Our solution is to introduce decoder modality dropout, and we found this to be the key for good multilingual AVSR performance. Here we'll briefly review Whisper-Flamingo's training setup. In stage 1, we make Whisper more noise robust, and we do this by fine-tuning the audio-only Whisper while adding noise to the audio. The noise includes speech, music, and babble sound, and we fine-tune all of the parameters. In stage 2, we inject the visual features into Whisper. We first freeze audio-only Whisper, and we add new trainable cross-attention layers into Whisper's decoder. The cross-attention layers attend to the visual features from AV-HuBERT, and we train the model on audiovisual inputs. To inject the visual information into Whisper's decoder, we use gated cross-attention, which is proposed by DeepMind's Flamingo model. Specifically, the equations are shown below. It's essentially just cross-attention. However, the alphas here are initialized to 0, meaning that tan h of 0 becomes 0, and the cross-attention is just zeroed out, leaving this layer to function just as the identity function. Over training, the model learns to adjust the alpha parameters, which makes the model start paying attention to the visual features via the cross-attention. Essentially, during the start of the audiovisual training, the model just trains on the audio input and then slowly learns to pay attention to the visual as well, making it into an audiovisual training. So this is a nice kind of smooth process to slowly integrate the visual information. mWhisper-Flamingo inherits the stage 1 and stage 2 from Whisper-Flamingo. We introduce modality dropout, where input modalities are randomly dropped during training. This better captures the cross-modality correlations while preserving the unique contributions of specific modalities. Modality dropout has been used in AVSR models previously to prevent models from over-relying on the audio modality. However, most methods use early fusion, while ours uses late fusion. Early fusion is used by methods such as AV-HuBERT, AV-Dataset, AV-SPL, etc. And in these methods, one audiovisual transformer encoder is used for both the audio and visual features. During modality dropout, the audiovisual encoder handles the incomplete stream. In late fusion, this is used by our methods, Whisper-Flamingo and mWhisper-Flamingo. Here we have separate audio and visual transformer encoders, serving as experts for each individual modality. We have separate cross-attention layers in the decoder. We propose decoder modality dropout, where we randomly replace the inputs to the decoder's audio and visual cross-attention layers with 0 vectors. This operation results in a 0 vector, but the output from the layer still incorporates the bias in the linear transformations. This forces the decoder to handle the incomplete stream. The encoders remain specialized on their specific modalities, while the decoder learns better multimodal integration. We define the probabilities of using audiovisual inputs, audio-only inputs, and video-only inputs as PAV, PA, and PV. This is a diagram of mWhisper-Flamingo. On the left, it's essentially the same diagram from mWhisper-Flamingo, where if we use audiovisual inputs, meaning no dropout, the decoder has cross-attention going to both the video and the audio features. Meanwhile, for video-only training, the model pays attention to the video features via the gated cross-attention. However, the audio features are replaced with the zero vector. Also, for audio-only training, the situation is flipped. The cross-attention layers pay attention to audio, but the video features are zeroed out. We found that PAV equals 0.5 and PV equals 0.5 work the best, meaning half the time we train on audio visual inputs, and the other half the time we drop the audio and the model trains on a video only input. We'll show the full results via an ablation study later. For the experiments, we trained on the MuAViC dataset, which is 1,141 hours of videos in 9 different languages. For the models, we have Whisper small, medium, and large. However, for the fine-tuned and versions and the mWhisper-Flamingo models, we use the small and medium sizes. For the metrics, we use word error rate for transcription, meaning lower is better. We also present results on different subsets of the languages. First, we have non-English averages, which include all of the non-English languages, or 8 of them, higher resource languages, which is a set of 4 languages, and lower resource languages, which is a set of 4 languages. These are all of the languages of videos in the MuAViC dataset, and we've categorized them into different groups. First, we have English with 433 hours. Then we have a group of higher resource languages with over 100 hours of data. This includes Spanish, French, Italian, and Portuguese. Next, we have lower resource languages, which has less than 100 hours of data. And for some of them, they have quite a small amount of data, including German, which is just at 10 hours. You can imagine that with such small amount of data, it's hard to train a good audiovisual model. So the performance on these languages is usually worse. Here's a schematic of the data distribution in MuAViC, and you can see that English is definitely dwarfing the size of the other languages. Some other differences to Whisper-Flamingo is that for AV-HuBERT, we use a version pre-trained on multilingual videos. Meanwhile, the previous model used a version just trained on English videos. And also here in stage 2, we fine-tuned the visual encoder, while the previous model kept it frozen. For the test scenarios, for clean, we test the model on the original audio without adding background noise. For noisy, we add noise to the original audio. Babble noise, specifically 30 speakers, is added to the original audio at a signal to noise ratio of 0. And this is a moderate level amount of background noise. Now we're going to compare the results in the clean setting versus the previous state-of-the-art models. We're comparing with 2 previous models in particular, XLA AVSR. This model adapts the multilingual audio SSL model, XLSR, and makes it into an audiovisual model. And there's Fast Conformer, which trains the model from scratch using CTC/R9T. And it also uses extra data from other video training datasets. Here we can see that XLA AVSR 2 billion has 4 bars. First, in blue is the average on the lower resource languages. Then in red is the average across all the non-English languages. In orange is the average across the higher resource languages. And in green is the average, or just the performance on English. Basically, as the amount of training data increases, then the word error rate improves and becomes lower. Fast Conformer only trained on the higher resource languages, hence it only has a bar in orange. First, we have our results for Whisper zero shot audio only without fine tuning. Whisper small is already performing better than XL AVSR 2 billion on the lower resource languages, getting an average on that subset of 37.5 versus the 41.9% from XL AVSR. It shows that out of the box, Whisper already has a strong multilingual knowledge, especially in the lower resource languages. For Whisper medium, it gets a better overall average non-English word error rate compared to the previous state of the art, 22.9% versus 26.4%. Moreover, fine-tuning Whisper also improves the word error rate. For example, for Whisper Medium, the performance improves to 20.1% versus 22.9% zero shot. And also for the English performance, it improved from 2.3% without fine-tuning to 0.74% with fine-tuning. And this matches the original English-only Whisper-Flamingo. It shows that we can make a multilingual model and retain the strong performance on the English subset. Finally, our audio-visual model builds off of the fine-tuned audio Whisper audio version, and it obtains performance similar to the audio-only Whisper. Also, it's state-of-the-art compared to the audio-visual models, which were trained on MuAViC. This is a breakdown per language of our best model, mWhisper-Flamingo medium, versus the previous state-of-the-art XL AVSR 2 billion. Across the board, we can see that our model with the yellow bars is getting better performance than the previous model. And we're seeing especially significant improvements on the lower resource languages. It shows that Whisper, thanks to its extensive pre-trained knowledge, can perform well in these languages. Also, we see an improvement on the higher resource languages and English as well. Finally, our model achieves better performance with fewer parameters, having only 1.4 billion versus the previous state-of-the-art of 2 billion. For the takeaway on the clean results, first of all, Whisper is a strong multilingual foundation model, and it's competitive even without fine-tuning. Building from Whisper, our mWhisper-Flamingo model obtains a new state-of-the-art for training on MuAViC, and it even outperforms Fast Conformer trained with extra videos, except French and PT. Finally, the performance improves when scaling from small to medium-sized models. Now I'll show the performance in the noisy scenario where we have babble noise at 0 SNR. We can see that immediately Whisper small zero shot is performing much worse. The average non-English performance is 71% versus previously it was 27% in the clean scenario. Fine-tuning Whisper small improves the average non-English word error rate from 71 to 55.3%. Finally, we introduce mWhisper-Flamingo, the audio-visual model, and we get a significant improvement on the non-English average from 55.3 to 50.4%, a 10% relative improvement. And we're getting a 16% relative improvement on the higher resource languages and 48% on just the English language. It shows that as the language has more video data available, the relative improvement is higher. So it shows that scaling up the video data could be a potentially fruitful direction for future work. We're also seeing a similar trend for the medium model, where we get 10.6% relative improvement on the average across the non-English languages. And for higher resource, there's also a 16% relative improvement and 40% relative improvement on English. Finally, we found an interesting takeaway that the smaller audiovisual models can beat larger audio models. For example, mWhisper-Flamingo medium beats Whisper large with more parameters on the average non-English performance. And also mWhisper-Flamingo small beats Whisper medium fine-tune on the higher resource languages. It shows that the better performance of the audiovisual models is not just due to the extra parameter count, but could also be attributed to the advantages of having the lip-based video encoder. We also evaluated on 6 different types of noise, including 3 different types of babble noise, side speech, which is a single speaker, music, and natural background noise. We averaged the results on 4 different languages, Spanish, French, Italian, Portuguese, and we specifically excluded English because we wanted to test the multilingual improvements. And we tested 5 different signal-to-noise ratios from -10 to 10, where -10 would be considered very challenging and 10 would be considered fairly light. Here we show the performance across the 6 different types of noise for the 3 models, zero-shot Whisper without fine-tuning, then a Whisper fine-tuned, and then our mWhisper-Flamingo model. And for each of these bars represents the average over 4 different languages and 5 different SNR levels, meaning 20 settings. And it sort of shows the holistic evaluation of that particular model on that type of noise. We can see that fine-tuning Whisper usually improves the performance across the different languages. And mWhisper-Flamingo in green is performing the best on all 6 different types of noise. So it shows that no matter the type of language or the SNR level, our audiovisual model is performing better across the board. We see a similar trend for the medium results, and the performance is getting better across the board when we scale from small to medium size. Finally, we have a ablation on the decoder modality dropout probabilities. The setting of PAV 0.5 and PV 0.5 works the best, where we achieve an average of 36.6 in the noisy scenario for 4 different languages. Without the modality dropout, the performance is much worse at 44.6. When we go from no dropout to adding dropout, we find that adding audio-only inputs, meaning we drop the video, doesn't actually help. So we have to have video-only inputs during the training process to get better performance. When we adjust the probabilities between all those 3, we find that using video-only inputs without audio-only inputs works the best. My takeaway is that since we fine-tuned the audio model in the stage 1 of training, the audio model is already well adapted to this scenario and doesn't need to be included in this process anymore. So during this stage of audiovisual training, the model needs to focus on combining the 2 modalities, and also it needs to have some video-only training for the video model to better adapt to this scenario. Now I'd like to show a demo video of the performance.
Cuando tenía 5 años y empezaba a leer, mi querido abuelo Carlos Felipe me regaló un libro de aventuras.
Et pourtant, les scientifiques des Nations Unies prédisent un effondrement des pêcheries d'ici 2048.
Le donne fanno, con qualche importante e luminosa eccezione, altre cose.
И единственный способ не жалеть в конце жизни – это поверить и прыгнуть.
If any child is found violating these rules, he is severely reprimanded.
Despite the heavy background noise, our model could pick out most of the words that each person was saying. However, it got some of the words wrong for the multilingual inputs. So there's definitely room for improvement in the future. To conclude, our model combines the strengths of Whisper, an audio model, and AV-HuBERT, a video model, using gated cross-attention. Our model obtains the new state-of-the-art for multilingual AVSR in 9 different languages, and our audiovisual model significantly outperforms the audio-only Whisper model on noisy audio. Our method's general and could work with better audio and video models in the future. We released the code models and demo on GitHub. Feel free to give it a try. Also, feel free to contact me if you have any questions. Thanks for your attention.